Alrighty. Hope everybody is doing well this morning. Got the doc cam fired up. Today we're going to talk more about the derivative. So this is, like I've been saying, one of the main objects of study in this class. So we're reaching kind of a plateau. You know, kind of the way any skill building class tends to go like this, where you start off a little bit gentle and you go through some preliminaries, and then things ramp up and you get to the main portion of the class. Some classes do that once, some classes do that once, then die back down, then do that again. Some classes go through 3 or 4 phases like that, but this is for us the first main plateau. You're going to notice that the homework for this week is a little bit longer than the homework, so normally they're expected to take around 180 minutes or about 3 hours. This week's will take about a half hour longer, so closer to 200 minutes by my estimate. So be prepared to put in a little bit more time, and I am prepared to offer as much help as you guys would like, but just be aware that we have approached the first real plateau in this class. The third, right? Yeah. Okay. More. So last time we spent most of our time on section 2.7. Today we're going to do a little mixture of 2.7 and 2.8. So 2.7 is where we define the derivative, and 2.8 is where we study the derivative as a function in its own right. So far we've only talked about the derivative in terms of giving a slope of a tangent line. So far we only have that kind of geometric thing, and we do have, of course, the limit definition. So I'll go ahead and kind of recap the two main concepts. So the derivative of f of x at x equals a, we use this notation for, which is also read as f prime of a. So this little like apostrophe notation here, which we've been using for the derivative, mathematicians call that the prime notation. So that's a standard way of saying the same thing as this. So if I want to refer to the derivative of a function, I might call it f prime, and I might call it the derivative. Either one of those would mean the same thing, and we use this symbol for that, which is defined by the limit of a plus h minus f of a all over h. So this should all just be stuff we remember from Monday's lecture. I'm going to show you a couple other equivalent definitions. So this limit is one way to get f primed of a. There are actually a couple of other ways. And then I'm also going to talk about when this thing exists and when it doesn't. So it's a limit, right? Which means it might not always exist. We've seen many limits which don't exist. And it turns out there's a little bit of terminology associated with that concept. We say a function is differentiable if this limit exists, differentiable at x equals a. Turns out to be a kind of similar concept to continuity, right? Like a function is continuous or not one point at a time. You look everywhere in its domain, you can check at any given point in the domain whether or not the function is continuous there. You can do the same thing with regard to differentiability. A function is differentiable or not one point at a time. So you can check each number in the function's domain and ask, is the function differentiable here? Is it differentiable here? And by that we would mean, does this limit exist? But before I get there, I want to give you the other equivalent formulations. So I held off on those on Monday to avoid confusion. And then we're going to solve a few problems. Before I get into that, are there any particular questions that you guys wanted to address? So again, we are getting to a kind of more challenging point of the class. I want to make sure that we're being as inclusive as we can. So if there's anything that you're wondering or feeling worried about, I'd like to talk about it.
I believe it was question 5. I guessed the graph by process of elimination, but I had a hard time understanding why exactly that was the graph.
Are we looking at question 5 in this week's homework or last week's homework?
This week's homework.
Okay. It's possible that we haven't covered that concept yet because a lot of these have you graphing a function and its derivative right next to each other, and we're only today going to start talking about how to think of the derivative as a function in its own right. But let me take a quick peek. Here. So let me alter my screen share a little bit so you can see everything here. Is this the one you're talking about?
Could you scroll down? Let me see.
So,
yeah, that one's one of them, but I think maybe it's number 4 then. Question number 4. Yes. So I was able to figure out the lines for the secant, but I just wanted to know. I just did process of elimination. I didn't really understand why. If I had to put it together, I know I would be in a bad situation.
all right, I think 4 and 5 might both be really good problems for us to go over today. I'm going to hold off for just 1 second though, because while we're recapping this material, happens to be the perfect place to introduce the other 2 little things I wanted to show you at the start of class. So as soon as I finish this, if you notice me not jumping back to those homework problems, be like, wait, you said you do those problems, and we'll do those problems. But real quick, before we do that, I want to define something for you. So here's the alternate definition of the derivative. The limit on the far right is literally the same thing as the limit on the left. It's just 2 different ways of writing it. So both of these are slopes, right? This is like y2 minus y1 over a plus h is x2 minus a is x1, and a plus h minus h is, or a plus h minus a is h. If you plug in a plus h for x here, this will become this. And as x approaches a plus h would approach a. In other words, as x approaches a, h would go to 0. These are 2 different ways of writing the same thing, and sometimes one is easier to work with than the other. So one of the example problems I'm going to do for you today, I want to do the calculation like this. Your book shows both of these to you in section 2.7, and I wanted to work just with this one on Monday so we didn't introduce any confusion. But these are two absolutely equivalent definitions. They mean literally the same thing. If you plug x equals a plus h in the second, it becomes the first. Okay. So if you start working a problem using this definition, and for whatever reason the algebra is just unmanageably nasty, you might consider working it with this definition. And then one other thing I wanted to show you beforehand. We say a function f of x is differentiable at x equals a if f primed of a exists, i.e. the limit above, let's see, the limits above exists. Right. So it's possible for those limits to not exist. Yeah, if the left and right limits don't agree, then the limits upstairs there, these guys, might not exist. If that's the case, then f primed of a doesn't exist because it's defined to be that limit. And if that's the case, then we say f of x is not differentiable. So think of differentiability as being a smoothness criterion. Functions which are smooth, don't have any jagged points, are differentiable. Functions that do have like a jagged point, think like the absolute value function, are not differentiable at that jagged point. They might be differentiable everywhere else because, like continuity, it's something that happens one point at a time. But it's possible for f primed of a to not exist depending on the function f and the number a that you're talking about. An example here. F of x equals the absolute value of x is not differentiable at x equals 0. And I'll use this limit definition here. Lim x goes to 0 of f of x minus f of 0 over x minus 0 for the absolute value function is the limit as x goes to 0 of the absolute value of x minus the absolute value of 0 over x minus 0, which is the limit as x goes to 0 of the absolute value of x over x. Oops, let me move this down a little. Okay. So I haven't gotten to the punchline here yet. I claim that this function is not differentiable at x equals 0. The way I'm going to show that is by looking at this limit and showing it doesn't exist, right? This is this limit with a equals 0 plugged in. And then from here to here, I'm just replacing f of x and f of 0 by what they are. F of x is the absolute value function, so f of x is absolute value x, f of 0 is the absolute value of 0. And then here I simplify. The absolute value of 0 is 0, and x minus 0 is just x. You may remember this function. We looked at him back when we talked about continuity. And remind you the graph of that function is, so here's what the graph of the absolute value of x over x looks like. If you look to the left of 0, if you look to the left of 0, he's down here at -1. And if you look to the right of 0, he's up here at +1. He has this big jump discontinuity at 0. So the limit as x approaches 0, from the left of this function is -1. And the limit as x approaches 0 from the right of this guy is +1. So the limit above, defining f primed of 0, does not exist. Right, I'm sorry, I should write it here, right? F primed of 0 would be this limit. But since that limit doesn't exist, f primed of 0 does not exist, which means that that function, the absolute value of x, is not differentiable at x equals 0. So take a second, make sure you've got all this stuff written down, right? The alternate definition of the derivative. So both of these definitions. The definition of differentiable function, what it means for a function to be differentiable. And then this example where we show that the absolute value of x is not differentiable. I want to do something back here in Desmos. But first I want to make sure you've got enough time to absorb all of this. So make sure you get everything written down. And then we can talk about any questions you have about this example. Then we're going to look at Desmos. And then we'll go to the 2 homework problems that Aubrey mentioned. So f primed of a, this is the definition we were playing with on Monday. This is an alternate definition. They're both slopes. And in both cases, we're sending the 2 points that define the slope to each other. Here I do that by sending h to 0. Here I do that by sending x to a. And if you plug x equals a plus h into this definition, it'll turn into this one. So you can see that they really are identical. Our definition here, a function is differentiable at the number a if f primed of a exists. That is, if the limit defining f primed of a exists. And it's possible for that to fail. And the absolute value of x is an example of a function for which that definition fails at 0. Everywhere else, absolute value of x is differentiable, but at 0 it's not. Why is it not differentiable at 0? Because f primed of 0 would be this limit, but this limit does not exist because the left limit and the right limit are not the same. So any questions about the definition or example there? Yeah, so Mary has gone and hit on the big one here. If a graph is continuous, is it automatically differentiable? That is a wonderful question. The answer is no. And let's see here. The green graph is the graph of the absolute value function. It is continuous. It's continuous at every point in its domain, including at 0. The limit as x approaches 0 from the left is 0. The limit as x approaches 0 from the right is 0. F of 0 does exist. It is defined, and it is equal to the value of both of those limits. So the green function here is indeed continuous, but it's not differentiable at 0. It's differentiable over here. The slope of the tangent line is definitely well defined over here. It would be 1. And it is differentiable everywhere over here. The slope of the tangent line over here would be -1. So if you were to plug in a equals -2 or -1 or -1/2 or -pi, any of those would work for the derivative. You could define the derivative at any of those x values and it would work out just fine. This is a continuous function. It's continuous everywhere in its domain, and its domain is all real numbers. So this function is continuous everywhere. But down here at 0, we have this sharp point, this hard corner. Even though we're continuous there, we're not differentiable there. So it turns out the blue graph you see here is actually the graph of the derivative of the green function. And it has this jump at 0 because the green function is not differentiable at 0. So one last little thing. This is a theorem, and it answers Mary's question beautifully. That's a wonderful question. Yeah. There are some implications here. It turns out if f of x is differentiable, at x equals a, then f of x is continuous at x equals a. However, it is possible that f of x is continuous at x equals a, but f of x is not differentiable at x equals a. So it's a one-way implication. And depending on your background with logic, that may be something you've heard of, or it may not be something you've heard of. If you're differentiable, then you are continuous. But it's not true the other way around. You can be continuous, but not be differentiable. So the absolute value function is an example of a function from the second sentence. That function is continuous at 0, but it's not differentiable there. It is impossible, though, to have the other thing. You cannot be differentiable without being continuous. So another way to write this is differentiable implies continuous, but continuous does not imply differentiable. One last way to think of it, differentiable means smooth, no hard corners. You can't be smooth if there's a jump or if there's a gap, like a hole. So differentiable means smooth, right? And the only way to be smooth is to also be continuous. However, you can be continuous without being smooth, right? You can be continuous and jagged, but you can't be smooth and jagged. So if you're smooth, you're definitely continuous. However, you can be continuous without being smooth. And the absolute value function is the perfect example for this theorem. This is an important theorem. There will almost certainly be a question on your first exam that measures how well you understand this idea. Okay. So let's move. That was a wonderful question, Mary, and it was perfectly timed. You set me up beautifully for this theorem, so thank you. First exam, we're getting close to, I guess we can take a second here. Yeah. I will let you know well ahead of time. We are a little bit behind the calendar because we had that holiday. We got slowed down a bit. So right now we are like right here, but it's actually this week. So next week we're going to start covering basic differentiation rules. The week after that we're going to cover the chain rule, and at the end of that week we will be ready for exam 1. So probably what we're going to do is at the end of next week I will send out the study guide for exam 1, and then either at the end of the following week or at the start of the week after that we will have exam 1. So let's turn our attention to those 2 problems we wanted to look at from the homework. We want to find the slope of the tangent and the equation of the tangent line, and then sketch some graphs. So let me write this down. This is homework 4, number 4. Find slope m of the tangent line for y equals 3 plus 5x squared minus 2x cubed at points 1, 6 and 2, 7. Write the equation of the tangent lines, sketch the graph. Okay. There we go. All right. So I'm kind of writing this with fewer words, but this is what we want to do. We want to find the slope of the tangent line, m tan, for this function at these 2 points. We want to give the equation of the tangent lines and sketch the graph. The function we're dealing with here is a cubic polynomial, which means we're going to have to be a little bit patient. Things are going to get a little bit hairy algebra-wise. It turns out that using the definition of the derivative to compute these things is a bit of a messy way to do it, but it's worth getting the practice. So we'll do the first point here, and I'll leave the second one to you because there's only so much time in the lecture. So we're going to have to run through this whole process twice, once per point. For the first point, point 1, 6, the slope of the tangent line is the limit as h goes to 0 of f of f of 1 plus h minus f of 1 all over h. We'll use that first step.
Assuming, sir, the first point is x equal to a.
Did I misread something?
Yeah, this is one. I said, yeah, they say where at the point where x equal to a.
Oh, they want the generic one. Okay. All right. Yeah, we'll do that. I get it. Okay.
Okay.
Okay. Here. So. So we'll get the general result, and then we'll plug values in for a to get those 2 points. We don't use the function notation here because they're just calling this thing y. So, well, we have to, right? So this thing here is f of x. Let me get a fresh sheet of paper so this doesn't get sloppy. So find m tan for y equals 3 plus 5x squared minus 2x cubed at x equals a, then find tangent line at 1, 6 and 2,7, then graph. Okay, sorry. So I won't be lazy or sloppy. Yeah, we'll do the whole thing like this. So the first part, all right, we've got part 1, part 2, part 3. The first part 1, I'm going to call f of x this function, so I can use my notation. Then the slope of the tangent line is f primed of a, and as Antoine pointed out, this means that they want us to do this in general, right? Not at a particular x value, not at a equals 1 or a equals 2, but they want us to do this to come up with a formula in terms of a. So this will be the limit as h goes to 0, f of a plus h minus f of a all over h. And f of x here is just the thing that they called y. I'll make sure I'm not being silly. That is what they asked for, right? Is this whole thing. Oh, that's Calc 2. They did ask for this whole thing, then we should do that. Yeah, at the point where x equals a. Okay. So what is this? This is the limit. I'm not going to have room here. This is the limit as h goes to 0 of f of a plus h. That's this thing with x swapped out for a plus h. So that's 3 plus 5 times a plus h squared minus 2 times a plus h cubed.
Can you adjust your screen, please?
Oh, yes, thank you. All right, here we go. So I was going to continue it over here, but I don't think there's room, so we're continuing down here. F of a plus h is this thing, because I take f of x and I swap in a plus h for x. Now I'll need to subtract off f of a. So that's minus 3 plus 5x squared minus 2x, a squared, f of a cubed all over h. So the work here is going to be in the algebra to cube this out. I may do that on the side. So I'm going to come over here. And we'll say that a plus h cubed, we'll do it like this. If you know Pascal's triangle, you can do this really quickly. But if you don't, then you need to FOIL it all out. That's a plus h times a plus h times a plus h. And then the first two, that's a squared plus 2ah plus h squared. And there's still one more here to distribute. So if I distribute the a across all of these, then I'll get a cubed plus 2a squared h plus h squared a. And then I distribute the h across all of these, and I get h times a squared. That's another a squared h plus h times 2ah is 2ah squared. And then h times a squared is h cubed. Okay, so this is the process for distributing everything out. First, I multiply these two to get this. Then I distribute my a times a squared is a cubed. A times 2ah is 2a squared h. A times h squared is h squared a. Then I distribute the h to everybody. h times a squared is a squared h times 2ah is 2ah squared, h times h squared is h cubed. So this is a cubed plus, I've got 2a squared h there and 1a squared h here, that's 3a squared h. And then I've got 1h squared a here and 2ah squared here, that's 3ah squared. And then I've got just the h cubed. And you can jump straight to this with Pascal's triangle if you know what that is. But that's going to be this piece. Everything else here is fairly easy to deal with. So let's go ahead and do it. This 3 minus this 3. We'll leave it here. We'll be real careful. I'm going to have my 5 times a squared plus 2ah plus h squared. That's foiling out the a plus h squared, minus 2 times this apparatus, a cubed plus 3a squared h plus 3ah squared plus h cubed. And then from that, I need to subtract this. I'll go ahead and distribute the negative. So that's going to be minus 3 minus 5a squared plus 2a cubed. All over h. Big, nasty expression. So let's take a second and pause here and make sure we're comfortable with what we've done so far. Any questions about what we've done so far?
No, sir.
Everybody's able to follow those algebra steps? It's not too bad, right? It's not too bad. It just takes a lot of writing. So then we can try to kind of collect terms and cancel things. I've got a plus 3 here and a minus 3 here. Those will go. I have a plus 5a squared here and a minus 5a squared here. Those will go. I have a minus 2a cubed here and a plus 2a cubed here. Those will go. So again, I'll be real careful on this just to make sure we're able to follow. I know this is not simple, so I'll write out everything except for the 3's. 5a squared plus, when I distribute this, I'll have plus 10ah, and when I distribute that, I'll have plus 5h squared. Then here I'll have minus 2a cubed minus 6a squared h minus 6ah squared minus 2h cubed. And then I've got the minus 5a squared plus 2a cubed all over h. You can see there are a few other things that will cancel. Minus 5a squareds plus 5a squareds. The a cubed, right? Minus 2a cubed plus 2a cubed. I think that's it though. I think pretty much everybody else is going to hang around. Are there any like terms I can combine? Well, I've got a 10ah here. Do I have anything else that is just ah? No. 5h squared here. Do I have anything else that's just h squared? No. A squared h, ah squared, h cubed. Nope, everybody else is going to stick around. So let's write this down. I've got 10ah plus 5h squared minus 6a squared h minus 6ah squared minus 2h cubed all over h. And what you notice is that in this form, once we've distributed and combined all the like terms we can, every term which hasn't canceled has an h in it. So I can factor that h out and cancel it with the h downstairs. Now, kitty. Yes, you're so sweet. So I'll factor out the h from the top. And what's left up here is 10a plus 5h minus 6a squared minus 6ah minus 2h squared. All of this is over h, and now those h's can be canceled. So this is the limit as h goes to 0 of 10a plus 5h minus 6a squared minus 6ah minus 2h squared. Kitty cat. And now I can plug in h equals 0 because there's no more h in the denominator. When I plug in h equals 0, this term will go to 0 because it has an h. This term will go to 0 because it has an h. This term will go to 0 because it has an h squared. So what's left? I've got 10a minus 6a squared. Right? Every other term there went to 0 because it had an h. So this is the slope of the tangent line to that curve at any x value a. This thing is the derivative as a function of a. And it's nice to get this formula. I know this seems like a lot of work, but now if you wanted to find the tangent line at any point, instead of having to do a fresh limit calculation, you can just plug in that a value to this formula, and it will give you the slope of the tangent line. Oh, cat, no. Sorry, my cat's chewing on power cords. No. You can't do that. You just can't. Okay? You're going to get hurt. Not an option, kitty. Okay? So take a second, make sure you've got everything written down correctly, and then I'd like to answer any conceptual questions you have. Okay. You got it. I love you. Annie, you want to come in? No? All right. Figure shit out.
Professor,
Yes.
if you were to ask us this a question like this one on the test, do we have to do all the work, or could we just take the derivative of the function and save basically just a lot of time doing that?
Well, yeah, so that's a question that's kind of being asked with a little bit of a priori knowledge. Right now, you shouldn't know how to take the derivative of the function by any means other than this. Right now, this is the only way we have to find the derivative. Now, if you've taken calculus before, then you might know some other tricks. On an exam, if I say, use the definition of the derivative to find blah, 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 then you have to do this.
Okay, so we couldn't use the power rule.
No, yeah, certainly right now we don't know the power rule, right? Now, if anybody who's taking this class for the first time right now has no idea what the power rule is, and we won't have that for a little while still. But the rule is if I tell you to use the definition of the derivative, you must use one of these limits. But if
Okay, thank you.
then you could use whatever else you had.
Okay, thanks.
Sure, of course.
I'm sorry, I must have missed something. Can you tell me how you got 10a minus 6a squared?
So are you comfortable with how we got to this line?
Yes.
So from here, I just plug in h equals 0.
Oh, sorry. Thank you.
10 goes away, this goes away, this goes away. No worries. What else are we thinking? Everything else feels mostly okay?
Will we be able to have these, do we need to have these memorized
No.
terms, essentially?
You need to have this definition memorized.
Right, okay.
But the limit work here is something that will be different for every function and every number. So no, you definitely don't need to memorize this process.
No, that's easy. It's just tedious, but that's the same definition that we've been using. So it's all good, right?
Yeah, exactly. Yeah, I could have used the other definition here, but for this particular problem, the algebra is nicer if we do it like this. It's still pretty unpleasant, but it would be more unpleasant with the other definition. Other questions on what we did here? Okay, so then let's come to the second part where we're writing down the equation of the tangent lines. So basically, in part one, we found that f of x equals 3 plus 5x squared minus 2x cubed has f primed of a equal to 10a minus 6a squared. And part two of my question says find the tangent lines at 1, 6 and 2, 7. So the first point, 1, 6, we have slope. How do I get the slope of my tangent line from what I have already done without going back and doing a fresh calculation?
Y minus y1 equals m times x minus x1.
That's what I'll use to write down the equation once I have the slope, but I need to know what m is first.
Oh, geez. Okay.
I'm sorry. So this guy is a, right? Your point of tangency is always a comma f of a. So your slope here is going to be f primed of 1, which according to what we did in part 1 is 10 times 1 minus 6 times 1 squared, which is 4. And now we'll use, just like Angelica was saying, we'll use that point slope formula. So the equation of the tangent line there's all sorts of bad jokes about tan lines out there. I'll spare you those. The equation of the tangent line is y minus y1, y minus 6, y minus f of a equals f primed of a, f primed of 1 is 4 times x minus a, or x minus x1, which is x minus 1. All right, and that's it. If the problem asks for this in like slope-intercept form, then you might have to solve this for y, but I don't think they did. I don't think they specified. And either way, it's not hard. Ooh, they do. Yeah, they've got it written y equals, so, and they changed the numbers on me since I reloaded this. So to finish this up, we would solve this for y. I can distribute the 4, so I'll have 4x minus 4, and then I add.
Sir, can you change the screen, please?
Oh, yes, sure. So I solve this guy for y now, and I get y equals 4x minus 4 plus 6 is plus 2. So just solving that point and slope equation for y. Okay, any questions on how I'm coming up with this? If not, then I'm going to continue to the second point, which is 2 comma 7. Again, here a equals 2, because this guy is always a. My slope is always f primed of a, so that's f primed of 2, which is 10 times 2 minus 6 times 2 squared, which is 20 minus 24, right? So that's minus 4. So the equation of the tangent line here is y minus y1, y minus 7 equals negative 4 times x minus 2. And that's part 2 sorted. I suppose we should solve this for y also, because they did ask us to do that. So if I distribute the negative 4 here, I get negative 4x plus 8, and then I add 7 to that. So y equals negative 4x plus 15. 8 plus 7, yeah. And then the last step was to graph this. We want to graph the function and both of the tangent lines. Graphing this is not easy. Graphing this cubic polynomial will require some work. And we might try to follow the techniques we learned in pre-calculus. And I don't know how well you guys remember those for graphing higher order polynomials. But you can work with the roots and the end behavior to get a nice picture of the graph, provided it doesn't have any weird turning points. We are a little bit limited in time, so I would throw this into Desmos at least. I would throw f into Desmos. Zoom it out a little bit. Yeah, because he does have these 2 weird turning points up here. Getting this graph without Desmos would be hard. So if when you get to this point on this problem, you're like, I don't know how to graph that weird polynomial, that's okay. Go ahead and use a graphing utility. And then we can graph the 2 tangent lines. And you see that he is indeed tangent to the graph right here at 1 comma 6. Yeah, 1 comma 6, that's our point of tangency. And then the other guy is y equals negative 4x plus 15. And he's at 2 comma 7. That's our second point of tangency. So this is the picture you're after. And I don't think that this green graph is something that you guys would be expected to come up with on your own. It's not an easy graph to get, frankly. You wouldn't be able to locate these turning points just yet, not on your own. Although we will be able to do that very, very soon. So any questions about how we got these tangent lines?
No, but it is a lot of work.
It is. It's absolutely a lot of work. I don't want to give you things to cheat yet, but you may notice a relationship between this expression and this expression. If I cover up the 3 here, the 10a is like 10x, and that's coming from the 5 times 2. This 5 times that power 2. And the minus 6a squared is coming from doing something to the minus 2x cubed.
That is insane. That's actually really interesting. Would it always be a minus a squared?
No, not necessarily. And I don't, like I said, I don't want to give too much away, but what I'm pointing at, or what I'm hinting at here, is that soon you won't have to do all that limit shit. Soon we'll have a way of doing this
Thank
that
you.
solve those limits. For now, though, we do need to be comfortable working with the limits. A big part of the first third of this class is getting you to a place where you're actually comfortable taking limits of difference quotients. But I promise after this homework, no mas. So,
If that were a test question, we necessarily wouldn't have to graph it. We would just need to prove it.
mhm,
And that way we're not using Desmos. Is that
Correct.
the idea?
yeah, if this were a test question, either I would not ask for the graph, or I would make sure that the original function is something you know how to graph already.
Yay. Thank you.
Yes. There are ways to go about graphing functions like this, right? If you can factor this, then you can use the end behavior and the local behavior near the roots to graph it. And for some cubic polynomials, that's manageable, but this particular cubic polynomial only has one real root and two complex roots. So this would not be one that I would expect you to graph by hand. But something like x cubed minus x, that we should be able to graph by hand. Other questions on this fella? Okay, so real quick, there's a little bit more good juju we can get out of this problem, and it's going to lead us in the direction that I wanted to spend the rest of today's lecture on. Look up at the top there where we've got f primed of a equals 10a minus 6a squared. So we're leaving example land now. We showed that f of x equals 3 plus 5x squared minus 2x cubed has the derivative f primed. Instead of writing an a there, I'm going to write an x there. Has f primed of x equals 10x minus 6x squared. Now you agree that this and this give the same information, right? The only difference is instead of writing an a for the variable, I'm writing an x for the variable. Usually we think of a as a fixed constant, and we think of x as a variable that's free to move around. What we do in section 2.8 is we start to study this object as a function in its own right. And I want to look at those two graphed together. So I'm going to get rid of these individual tangent lines. Whoops, cubed. On the same graph. And I want to make them different colors so they kind of stand out. How about red? I would like to take a second and compare the red graph to the green graph. Does anybody see anything relating the red and green? So like, let's look over here. From negative infinity to 0, the green function is decreasing. We all agree with that? We're decreasing here, we're increasing here, and we're decreasing here, right? What do you notice about the red graph for those same x values? Well, over here, from negative infinity to 0, the red graph is negative. And then between these two hills, or between that valley and that hill, the red graph is positive. And then right here, where the green graph goes from being increasing to decreasing, the red graph goes back to being negative. What is this? What is this x value? 1 1/3. What is that? That's 4/3. 5/3. Yeah. Okay. So notice that the place where the green function goes from being increasing to decreasing or decreasing to increasing are x-intercepts for the red function. The red function is called the derivative of the green function, and it encodes all of the increasing and decreasing information for the original. If the red function is above the x-axis, then the green function is increasing there. And if the red function is below the x-axis, then the green function will be decreasing there. I can actually pull this 3 off to make it a little bit easier to see. So this red function is still the derivative of this green function. I just modified the green function a little bit. Notice that where the green is increasing, the red is positive. And where the green is decreasing, the red is negative. So I want to use all the notation from your textbook. This is a nice example illustrating the first main point. Observe the x values where f primed of x is less than 0 are x values where f of x is decreasing, and the x values where f primed of x are positive are x values where the original f of x is increasing. That's a big deal. In fact, this is how in every math class from here on, Calc 2, Calc 3, differential equations, linear algebra, whatever you do, this is how you figure out where a function is increasing and decreasing. Up until now, you've had to have a good picture of the graph, and you've had to guess at those turning points. No more. Now you can tell me for sure where a function is increasing or decreasing by figuring out where its derivative is positive or negative. And this is also going to help us find minima and maxima, because those turning points, places where you go from increasing to decreasing, are places where minima and maxima occur. I'm going to get into this gently. We showed that theorem. We did these calculations. I do not want to talk about higher order derivatives yet. Differentiability implies continuity. Wow, okay, they do jump straight to that, huh? That's a bummer, and they don't talk about increasing or decreasing at all. Okay. So we're going to talk more about this increasing, decreasing, minima, and maxima stuff when we get into chapter 3 and we talk about, when we get into chapter 3 and we talk about applications of the derivative. But all of this is coming from the fact that this guy gives the slope of the tangent line. So we're going to talk about vertical and horizontal tangents. Well, actually, I'll just say fact. If f of x is differentiable at x equals a and f primed of a equals 0, then f of x has a horizontal tangent line. At x equals a. I'm not calling it a theorem because it's really not a powerful enough result to call it a theorem. We know that f primed of a is the slope of the tangent line at x equals a. So if f primed of a is 0, then you have a horizontal tangent line. And if f primed of a is plus or minus infinity, then f of x has a vertical tangent line at x equals a. And horizontal and vertical tangent lines are a little bit special. Here, we also need, f of x has a vertical tangent line, provided f of a exists. So I want to show you some examples of interesting tangent lines, and I want to show you graphs of f overlaid with graphs of f prime, so you can start to see how they're connected. I think maybe maybe a nice first example here would be x cubed minus x. I mentioned that this is a cubic polynomial that you should be able to sketch the graph of on your own. Let's find f primed of x and graph them together. So f primed of a, I will calculate using my definition. And then I could swap a for x, or I could just do the calculation directly. So f primed of x would be the limit as h goes to 0, f of x plus h minus f of x all over h. You could do it either way. I'm going to do it the second way. F of x plus h minus f of x all over h. What does that look like? That's the limit as h goes to 0 of f of x plus h is x plus h cubed minus x plus h. And then f of x is x cubed minus x. And putting those things in big parentheses like this is a good idea. At least the second one needs them, so you remember to distribute the negative. Am I scaring anybody here by swapping in x for a? Are you guys comfortable with what we did? It's the same thing I did at the end of the last problem, where we had f primed of a equals 10a minus 6a squared. And I said, okay, well then f primed of x is 10x minus 6x squared. I'm just taking one variable and switching it with the other. So the functions still describe the same information, it's just a different notation. Are we okay with me saying this? F primed of x equals this?
Yes, sir.
Any questions about what that means or how that could be different from this?
It wouldn't hurt if you explain.
So the reason I'm doing this instead of writing an A here, writing an X here, instead of writing an A here, writing an X here, A here, X here, is because I want to graph the function and its derivative on the same coordinate axes. So I need to use the same variable for both. That's all, right? So instead of calling one function f of t and another function f of x, I just call them both f of x. Same sort of thing. Because I intend to graph them on the same coordinate axes, I want to use the same variable for both. It's just a label, right? Rose by any other name smells just as sweet. Well, f prime of a gives me the exact same information as f prime of x. Does that help?
With practice, it would make more sense.
Okay. So then let's just kind of hold on to our pants and go through this calculation and see what we come up with. The x plus h all cubed, I'm gonna do that quickly. That's x cubed plus 3x squared h plus 3x h squared plus h cubed. And then minus x plus h, that's minus x minus h. And then I distribute this negative, and that's minus x cubed plus x. So if you want to know the trick for cubing things like this out very quickly, come by my office hour this afternoon. I'll show you. It's called Pascal's triangle. It's very nice. So what lives and what dies? Well, this x cubed, he's going to get eaten up by this x cubed. I've got a plus x here and a minus x here. They will consume each other. And everything that's left here is going to be 3x squared h plus 3x h squared plus h cubed minus h, all divided by h. So now I can factor out an h from the top. When I do that, what's left is 3x squared plus 3xh plus h squared minus 1. And this is all over h, so then I cancel the h's, and I get lim h to 0, 3x squared plus 3xh plus h squared minus 1. And now since there are no more h's in the denominator, I can just plug in 0 for h. This piece will go to 0. This piece will go to 0. So I just get 3x squared minus 1. Okay. So f prime of x is 3x squared minus 1. If I had done this with the a's instead of the x's, I would get f prime of a equals 3a squared minus 1. Only difference here is that it comes out with the variable x instead of the variable a, which is nice because then I can graph them both on the same coordinate axes. Since I said you should be comfortable graphing x cubed minus x by hand, I think it's only fair that I do that. So let me dig up a sheet of fresh paper. Let's do it. How do you graph x cubed minus x? Well, there's two things. First, we should factor it. That's x times x squared minus 1, which is x times x minus 1 times x plus 1. So first I factor out the common factor of x, and then this piece which is left over I factor as a difference of squares. This tells me I have x-intercepts at 0, This tells me I have an x-intercept at 1. And this tells me I have an x-intercept at -1. And also my end behavior looking like what? So it's a degree 3 polynomial, odd degree. So the end behaviors are going to be opposite on either side, up on one, down on the other. And since the lead coefficient is positive, the end behavior will be down on the left and up on the right. So that's all I need to get a good graph of f. Each of the roots are multiplicity 1 roots, so we will cross at each of those rather than bouncing. I'm going to label this out here as -1, and somewhere around that same distance, I guess, here-ish, as +1. Ah, shit, that's close enough. My end behavior I know is down on the left and up on the right. And since the root at -1 is coming from a multiplicity 1 factor, I know I will cross the x-axis there. And since I'm arriving from below, I know that means I have to cross like this rather than like this. I'm going to come up here. I've got a root here at 0, an x-intercept right there. So he will cross like this there, again, because this is a multiplicity 1 factor. And then when I get over here, I have to cross like this, because this is a multiplicity 1 factor. If any of these multiplicities were even, then we would bounce off the x-axis there. So now I can fill in my nice graph. The only way to connect these pieces like this is like that. So that has to be what the graph of x cubed minus x looks like. Gotta look like that. Can't look like anything else, just according to his factors. If you don't remember how to do this, you should go back and look at your pre-calculus notes. If you don't have those, then you should come by office hours and talk to me. F primed, the derivative is 3x squared minus 1. I can force factor out a 3, and what's left is x squared minus 1/3. And that can be factored as a difference of squares. That's x minus the square root of 1/3 times x plus the square root of 1/3. So f primed, and I will use a pencil to draw the graph of f primed, is a parabola. It opens up because the lead coefficient here is positive, and it has roots at plus and minus the square root of 1/3. Now you can be forgiven if you don't know where plus and minus square root of 1/3 are. The negative square root of 1/3 is right here. The positive square root of 1/3 is right here. He has a y-intercept of -1, which is also the vertex. And the graph of f primed looks like this. All right, so the pencil is f primed and the pen is f. What do you notice? Well, over here, my original function, oh, did I do this right? 3x cubed minus 1 should be increasing, so it should be positive, right? Did I fuck this up? X cubed minus 1. Right here, where f primed is equal to 0, I have horizontal tangents on the original. Right here, where f primed is 0, I have horizontal tangents on the original. In here, where f primed is negative, my function is decreasing. Here, where f primed is negative, my function is decreasing. Out here, where f primed is positive, my function is increasing. And over here, where f primed is positive, because it continues out like this, my function is increasing. So the ability to see the connection between the graphs of f and the graphs of f prime, kind of tricky, not super easy, but it is manageable. You can actually start with just the graph of f and sketch the graph of f primed reasonably well, even if you don't have a formula for f primed. But here we had a formula for both. How am I doing on time? 11:08. All right. So this might be the example with which we conclude today. I want you to think long and hard about how we could get the pencil graph from the pen graph without having a formula for the pencil graph. And then at the start of class on Friday, we're going to pick back up with more examples like these, because this is the last few problems in your homework. They all kind of look like this, or some variation on this. The connection between where f primed is equal to 0 and where f has horizontal tangents is very important. So you notice here where f primed is 0, f has horizontal tangents. And also, anywhere you look that f primed is negative, the original function will be decreasing there. Why? Well, because f prime being negative means the slope of the tangent is negative. This slope is equal to this y value. So I want you to start trying to think, how would I start with the pen graph and get from it the pencil graph? How would I start with the original function and start drawing a graph of its derivative? The trick is to think about slopes of tangent lines, of course, because that's what f prime does. It outputs the slope of the tangent line to the original. All right, so continue working on this week's homework. It's not terribly bad, but it is longer than our homeworks so far. Not by a lot, by about 30 minutes. But it's going to take more time and probably a little bit more effort also, not just more time, but the concepts here are building. Please take this week's homework seriously. It's not an easy one. And if you invest the time this week, it will pay off tenfold next week and the week after for the rest of the semester. These ideas are the ideas that are going to dominate our thinking for the remainder of the term. So think of this as like get real moment, right? This is the get real moment for this class, like in college algebra when they introduce logarithms, or in trig pre-calc when we start dropping the definitions of sine and cosine in terms of the unit circle. This is that get real moment for Calc 1. Now you've got the derivative. You see the connection between the derivative and the original function, and you have the tools you need to calculate and graph both. So this is time to get serious and really practice and make sure that your brains internalize these concepts. If you have anything that you would like to talk about, I have an office hour this afternoon from 1 to 2. Remember, the way you get there is go to our Canvas page and then click on the office hour link. I do have a waiting room system set up there because people can come and talk about private things with me. So if you're not immediately admitted into the office hour from the waiting room, please just be patient. Maybe a few minutes depending on what I'm doing with other people. So just click that link, you'll be added to the waiting room, and then hang around for a minute for me to admit you. If you run out of time or patience or whatever, you can always send me a Canvas message. You don't need to worry about doing the here for attendance thing. That's okay, that's just the first couple weeks. But if you have any questions, come see me in office hours, or send me a Canvas message or an email. Please don't suffer in silence. If you're having a hard time with something, don't just struggle with it. Talk to me. I would prefer that you talk to me. The tutors are good too. You can get a hold of the tutors through the links on Canvas, and they will help. But I think it would also be a good idea, if there's anything that's giving you a tough time, to please make a point of talking to me, either in office hours or via email, because I'm the one teaching your class. I really want us to be on the same page, and I think you probably really want that too. Any last minute questions here before we go? Alrighty, then I'm going to go ahead and end the meeting here. I hope you guys have a lovely rest of your day. Grind on that homework. Grind on it seriously. Work hard. And I will see you on Friday.